Chapter 6 is about polygons and parallelograms, and Section 1 is about properties and attributes of polygons. So by the end of this lesson, you should be able to classify polygons based on their sides and angles, and you should also be able to find and use the measures of interior and exterior angles of polygons. So a polygon is a closed plane figure bound by 3 or more line segments. The fact that they tell us it's a plane figure means that it's two-dimensional. It has to have at least 3 line segments, so a triangle is the smallest polygon you can have. Each segment that forms a polygon is a side of a polygon. The common endpoints of 2 sides is a vertex, and a segment that connects any 2 non-consecutive vertices is a diagonal. So this picture here illustrates you have a couple sides here. A vertex is where 2 sides come together. We got 5 of them for this one. And then a diagonal is anything that connects something that's not already connected. So if I was to connect like E and B or E and C, but I can't connect E and A because that's already a side. So naming polygons, some of these you guys are very familiar with, other ones probably not so much. But you can name a polygon by the number of its sides. So hopefully we all know about triangles. Quadrilaterals, quad means 4. So that includes like squares, parallelograms, rectangles, all that stuff that we're familiar with. Pentagon is 5. Hexagon is 6. Heptagon is 7. Octagon, think like octopus has 8 legs. Nonagon sounds a lot like 9. Decagon is 10, think like decade. Dodecagon is 2, and then 10 more, so 12. And then an n-gon polynomial, so anything after 12, we just call it whatever it is, gon. So like a 13 would be a 13-gon. Some of the other ones have special names, but these are the ones that you should know about. So for an example, tell whether each figure is a polygon. If it is a polygon, name it by the number of sides. So in order to be a polygon, remember that you have to have a closed plane figure, which everything's going to be 2D, bounded by 3 or more line segments. That means that they need to be straight. A line segment cannot be curved. So if we look at this one, we have a closed-in figure bound by several sides. This one is a polygon. And it's bound by 1, 2, 3, 4, 5, 6. So if we go back to this, 6 is a hexagon. If we look at this, same thing, it's closed in and all of our lines are straight. So this again is a polygon. And it has 1, 2, 3, 4, 5, 6, 7 sides. So again, we go back, it's called a heptagon. And then this moon-shaped one, it has 2 curved sides. That's not allowed, so this is not a polygon. Other examples of things not being a polygon would be if it wasn't totally closed in. So let's say we made kind of a triangle, but this length wasn't long enough. That's not closed in. It would also not be a polygon. Another one that they like to show often is if something looks like this. So even though it has several sides, it overlaps other sides. So it needs to be a closed plane figure. And in this case, it's not closed in because it has basically 2 enclosures here. So all 3 of these reasons are reasons why things are not polygons. So a regular polygon is what we're used to. If I told you to draw a pentagon, chances are it would look something like this. A hexagon, chances are it would look something like that. So a regular polygon is when all the sides are congruent and all the angles are congruent. So this says all sides are congruent in an equilateral polygon. That word equilateral we use with triangles. All the angles are congruent in an equiangular polygon. And a regular polygon has both. It's equilateral and equiangular. So a polygon can be concave or convex. A concave polygon is if any part of a diagonal contains points in the exterior of a polygon. If no diagonal contains points in an exterior, then the polygon is convex. Regular polygon is always convex. So I think of concave as if something caves in. It has like a space like this here, this space that you have outside of this four-sided figure. So it says that you need to draw a diagonal. So a diagonal, remember, is between two vertices. And this diagonal is outside of my polygon, so that makes it concave. Where here, if I take a look at all my vertices, the only diagonals I can draw are inside my quadrilateral. So let's take a look at all these. If we take a look at this one, we have 4 vertexes. If I start drawing my diagonals, I can only make 2, and they're both inside. So this has to be convex. One like this, however, if I start drawing my diagonals, I have some that are inside, like these, but then some that are outside, like that one. So because of that, this has to be concave. This one would be convex. All the diagonals are on the inside. I want you guys to name these 4 over here, and we'll discuss them in class tomorrow. So tell whether each polygon is a regular or regular, then tell whether it is concave or convex. So, regular or irregular. Regular means all congruent angles and congruent sides. Irregular means not. And then concave or convex we just talked about. So if we take a look at this first one, all the sides are exactly the same length. So that is the first checkbox. But my angles are different. Now those 2 angles are the same and these 2 angles are the same, but not all 4 of them are. So this is irregular. But then if you take a look at all of your diagonals, we can only draw 2, and they are inside this polygon. So that means this is convex. This next one here, take a look at the sides. It doesn't tell us anything about equal sides, but we have all of these equal angles here. So even though it has the angle part down, that doesn't help us with regular because it doesn't have equal sides. So this one is also irregular. And then let's talk about concave or convex. Remember, you got to find 2 vertices that when you draw a diagonal through them, they're outside of your polygon. And in this case, it has 4 diagonals that would be outside. So this is also concave. And then we have this one. So it tells us that we have congruent sides, and it tells us we have congruent angles. So this fits both of our stipulations. This is a regular polygon. And if we draw our diagonals, they're all inside, so this is also convex. So interior angles. Every polygon has a specific number of degrees that its angles add up to, and it's the same whether it's regular or irregular. Hopefully a triangle is committed to memory. You know that every triangle adds up to 180 degrees, and it doesn't matter what the triangle looks like. It could be obtuse, it could be acute, equilateral, equiangular. It will always add up to 180 degrees. So kind of a cool thing to do is, if you take a look at some of the other shapes we have and break them up into triangles, you can come up with a correlation. So a triangle is only made of one triangle, and it adds to 180 degrees. Any quadrilateral that you make, this weird shaped one, if I make a square, if I make a long rectangle, you can get 2 triangles out of it. And the total number of degrees that a quadrilateral always adds up to is 2 times 180, or 360. Every single time. Every pentagon that you can think of, you can split up into 3 different triangles. even if it's a regular pentagon, kind of like one of the house looking things, you can split this up into 1 triangle, 2 triangles, and then 3 triangles. So the total number of degrees in a pentagon is 3 times 180, or 540 degrees for every single one. A hexagon can be split into 4 triangles. Doesn't matter what it looks like, you can always get 4 triangles out of it. So the number of degrees is 4 times 180, or 720 degrees. So if I give you any type of polygon, it's going to have that many sides on it. Hopefully you notice there's a pattern here, that it's the number of sides minus 2. That's how many triangles you can get out of it, and it's always going to be that times 180 degrees every single time. So that brings us to a nice little theorem. In each convex polygon, the number of triangles formed is 2 less than the number of sides. So the sum of the angle measures is n minus 2, so this is number of sides, times 180 degrees. So we have something called the polygon angle sum theorem. We already had the triangle angle sum theorem. This works for every single polygon. So find the sum of the interior angle measures of a convex heptagon. So remember, heptagon means 7 sides. So our formula says that we're going to do n minus 2 and multiply that by 180 degrees. So I'm going to do 180 times 5. If you multiply that together, you end up with 900 degrees. So every single heptagon has exactly 900 degrees in it. Then find the measure of each interior angle of a regular decagon. Remember, decagon sounds a lot like decade. It has 10 sides. So if we plug it into our formula, 10 minus 2, I'm going to end up doing 180 times 8. So that gives me 1,440 degrees. Let's do one more. It says find the measure of each interior angle of this pentagon, A, B, C, D, E. So in this pentagon, I know that all of these angles have to add up to a certain number of degrees. So remember, it's 180 times pent, which is 5, minus 2. So I'm going to do 180 times 3. I know that all of those angles have to add up to 540 degrees. I should say times 3. So I have angle A, which is 35C, plus angle B, which is 18C, plus angle C, plus angle D, plus angle E. And all of this has to add to 540. So since all of these have a C next to them, we can just add 35 plus 18 plus 32 plus another 32 plus another 18. So we have 135C has to total 540 degrees. If we do a little algebra, we will end up with C has to equal 4. So now remember, it wanted us to find the measure of each of these angles, so that means we need to plug it back in. So angle A, I'm going to do 35 times 4, giving me 140 degrees. Angle B, I'm going to do 18 times 4, gives me 72 degrees, and there's another one over here. And the last one, I got to do 32 times 4, 128. Make sure you do a quick check. Add all those up. They should total this 540. So now let's talk about exterior angles. In the polygons below, an exterior angle has been measured at each vertex. Notice that in each case, the sum of the exterior angles measure 360 degrees. So each one of these exterior angles added together gives me 360. Even this weird shaped pentagon, They all add to 360. And it's because you're making it all the way around in a circle. So another theorem. The polygon exterior angle sum theorem says the sum of the exterior angle measures of a convex polygon is 360 degrees. And this is saying that you only have one at each vertex, so you can't measure like this angle and this angle. You just have to choose one of them. So let's do some problems. It says find the measure of each exterior angle of a regular dodecagon. So remember, a dodecagon means it has 12 sides. So if it has 12 sides, that means it has 12 exterior angles. I could draw it out and draw the exterior angles on there, but the number of sides equals the number of exterior angles. So if I want to split a total of 360 degrees into 12 angles, all I have to do is divide, and I'll end up with 30 degrees. So each exterior angle has to be 30 degrees. Now, not all of them will be that easy. This one told us it was regular, so that meant that every angle measure had to be exactly the same. This one they give us, the angle measures are not the same. But again, I know that all of these added up have to total 360 degrees. So we're going to do it just like we did the problem a little bit ago. Add them all up. Set them equal to 360 degrees now. I don't care what kind of shape this is because everything has to add to 360 regardless of the shape. So then I'm going to add 33, 16, 10, 28, 15, and 18. So I end up with 120b equals 360. Do a little algebra, I'll divide 360 by 120 and get that b has to be 3. That's all it wanted us to find the value of b, so we're done. If it asks for each angle measure, you know we'd have to plug that back in, but luckily we don't. So that's it. You should be able to classify polynomials or polygons based on their sides and angles, and you should be able to find the measures of exterior and interior angles. Make sure you write down any questions you have, and we can go over them in class tomorrow. Have a good night.